Alright, so now let's go to what is called the Cayley-Hamilton theorem. So we will be using the assured upper triangulation theorem and the matrix multiplication, nothing else. So let's look at the definition of what is the Cayley-Hamilton theorem. So given A, which is n cross n, we compute P lambda or P of x, which was nothing but determinant of xi minus a, the characteristic polynomial. All right. So it is a polynomial of the type x to the power n plus a n minus 1 x to the power n minus 1. There will be plus or minus signs, so I am not putting about a n minus 1 anything, plus a1 of x plus a0. This is what the polynomial is going to be. Since the matrix is n cross n, what we are saying is that it is a polynomial of degree n. Fine, that is more important for us. Fine. So that is the characteristic polynomial. We have been computed some of them for eigenvalues and so on. Fine. What Cayley-Hamilton theorem says, that this theorem implies that we can replace x. So if we replace x by a and compute a to the power n plus a n minus 1 a to the power n minus 1 plus so on plus a1 of a plus a0 of I. This is a matrix identity that we are looking at a matrix, all right, matrix computation. All right. There it was looking at x as a unknown or x as a variable, and we are looking at a polynomial in x with coefficients come as ai's, all right. Now you are looking at powers of a and then computing something. It says that this is same as the 0 matrix. This is what the Cayley-Hamilton theorem says, that if I look at this, then it is 0. Fine. Proof is simple. Let us go to the proof. What we know is that since it is a characteristic polynomial, so the roots of this are the eigenvalues. So I can write P of x as x minus lambda I product I is equal to 1 to n. So these are the eigenvalues where lambda 1, lambda 2, lambda n are the eigenvalues of A. All right. So what we have learnt? Schur's theorem says us, Schur's theorem implies I can write A as u t u a star, where u is unitary and t is upper triangular, and not only that, it also tells me that the diagonal entries of t. So if I look at t, then t can be written as lambda 1, lambda 2, lambda n, 0, sorry, upper triangular, so I am writing, so 0 is here, I do not know what it is. Is that okay? So this is important, that what we are saying here is that if I am writing t as Tij, fine, n cross n, then Tii is equal to lambda I. I can rearrange my eigenvectors, or I can rearrange the columns of u. I can rearrange the columns of u in such a way that I get lambda 1 as the first entry here, lambda 2 as the second entry, and lambda n as the second entry. Fine. Recall, when I looked at diagonalization, what we had done was we wrote P and we showed that A of u1 is equal to d1 u1, A of u2 was d2 of u2, and so on. So I could rearrange them depending on the matrix P that I take, all right. So there is just a rearrangement or permutation which will give me this part. So now I want to understand, I know that A is this, what happens to A square and so on. So if I look at A square is nothing but ut u star into ut u star, which is same as u times, which is same as ut times u star u t u star, which is, so this part is identity in, so this gives me u times t star u star, all right. fine. So therefore, I can write this matrix as the left hand side LHS as I just multiply everything by u on the left and u star on the right. Is that okay? I do that. So what I do? I multiply here everything and then look at things. Is that okay? So a to the power n from here, if I look at here, what I get is u times t to the power n u star plus a to the power n minus 1 is a n minus 1, a to the power n minus 1 will again u t to the power n minus 1 u star plus so on, plus a1 it will be u t u star plus a0 of I. This is what the left hand side is, fine. So this is same as the left hand side is also equal to, I can take out a u outside, t to the power n plus a n minus 1 t to the power n minus 1 plus so on, plus a1 of t plus a0 of I times u star, because u times u star is identity. U was an unitary matrix, all right. So this is how unitary matrices are very helpful to us, that we can do a lot of things. In place of going to the inverse, I can just use transpose or conjugate transpose and do the work, all right. So now we are looking at the left hand side, which is this. So now we need to compute this part for us, and from where did we get it? I am looking at p of x as this. Is that okay? So p of x was equal to this. So I would like to claim that if I look at p of t as product I is equal to 1 to n t minus lambda I of I, then this is equal to this expression that I have, all right. Why I am saying this? Because let us go back and see what we had was this is equal to this part we are saying. So we are saying that px is equal to product I is equal to 1 to n x minus lambda I, fine. To get this expression in A, we replaced x by A, all right. So in this expression, I am replacing x by A, but this is same as this, which is same as this, is an identity. This is an identity in x. If something is an identity in x, I can replace x by any object that I want to make things meaningful. So I can replace x here by A here. Is that okay? That's more important for me. I can replace, since this is an identity, there is an identity here going like this. So I can replace x by A, and I have to replace the constant by constant times identity to make sense of it. So this is what we have done, and I have done nothing else. So I have written this pt as this. Is that okay? So now let us compute this product I is equal to 1 to n t minus lambda I of I, and we are done. So let us look at this product very nicely. What we have is t, we wrote it as lambda 1 star lambda 2 till lambda n. This is what we wrote. So I want to compute what is t minus lambda 1 of I, and let us compute t minus lambda 2 of I, and so on. I want to compute this. Is that okay? So what is t minus lambda 1 of I? Look at t minus lambda of 1 I. The first column is 0, all right. Second column, if I look at, it is a star here, lambda 2 minus lambda 1, 0 here, and there are some things here. So this is lambda n minus lambda 1. This is the matrix this. What is this matrix? This matrix, if I look at the second matrix is lambda 1 minus lambda 2, 0 here, 0 here, 0, a star here, 0 here, because this entry is lambda 2 minus lambda 2, this entry is lambda 1 minus lambda 1, 0 here, and I have something here which will give me lambda n minus lambda 2 and a star here. And there are so many things here which are t minus lambda 3 of I, so on till t minus lambda n of I, all right. So I am just looking at this matrix product and nothing else. So be careful, don't get nervous, everything is nice here. So if I multiply this matrix, this column with this matrix, what do I see is, it is lambda 1 minus lambda 2 times the first column. So it is lambda 1 minus lambda 2 times, so if I write this as, or let me write t minus lambda 1 of I itself, look at the first column of this, plus t of t minus lambda 2 of I the second column, and so on. All right, fine. I am just multiplying these two matrices. I am not bothered about this part. I am just trying to understand the product of the first two matrices. So it is lambda 1 minus lambda 2 times the first column, which is all 0. Now it is 0 times everything else. So this will give me that this implies the first column of this product, whatever it is. So if I write this matrix as B of B is 0 vector. All right. Here itself it is 0. I still get 0 here. Is that so? I have not got anything extra. Let us look at the second column of B. Second column of B. If I look at the second column of B, I am multiplying by a star. So I am multiplying a star to t minus lambda 1 of I, the first column, and then again it is 0 times everything else, 0 times something. All right. Look at here, it is 0 times, fine. So I have got 0 times something here. A star is the first entry, but then rest everything is 0. So I am multiplying the second column here to 0, second column, third column to 0, fourth column is being multiplied by 0. All the columns here are being multiplied by 0. Is that okay? Fine. So therefore this is also, this implies that the second column of B is 0 vector. All right. Fine. So what you have shown is that if I multiply the first two, what I get is I get 0 in the first column, 0 vector in the second column. Earlier I had only 0 in the first column. After multiplication I get 2 part to be 0. So what we are getting is that I have got in B, so if I look at this B part, I have got 0 vector here, 0 vector here, fine. I do not know what is there for me here, fine. There will be some entries here on the diagonal, I do not know. Now I want to look at t minus lambda 3. So t minus lambda 3 means it is lambda 3, t minus lambda 3. So it is lambda 1 minus lambda 3, 0, 0, 0, a star here, lambda 2 minus lambda 3, 0, 0, 0, a star here, a star here. This is 0 because of lambda 3 minus lambda 3 and zeros here and so on, fine. So this corresponds to my matrix t minus lambda 3 of I. Just multiply it again. Since the first two columns are 0 here, fine. This part, the top first two rows of this on the right hand side does not give me anything. So what I will have is that this product will give me 0 in the first column, 0 in the second column, and 0 in the third column. Is that okay? So at each stage I am increasing the 0, the columns having 0 entries, and therefore finally I will get that the whole matrix is 0. Is that okay? So try that out yourself, prove it yourself. I have given you the idea, I do not want to spend time there, just complete it yourself, fine. So try that out. So I would now like to write the statements here which are important for me. So theorem, the statement of the theorem, let me write. Cayley-Hamilton theorem, I am writing it again. Fine. So let A belong to Mn of C, then A satisfies its own characteristic equation. So equation means characteristic. What is the characteristic equation? Characteristic equation is nothing but x to the power n plus a n minus 1 x to the power n minus 1 plus a1 of x plus a0 is equal to 0. That is the characteristic equation. It says that A satisfies its own characteristic equation. It means that a to the power n plus a n minus 1 a to the power n minus 1 plus a1 of a plus a0 of I is 0. So this is what we proved. Is that okay? Fine. So this is satisfied as a matrix identity. That's more important. I am not equating this at x. What I am saying is that I am not equating it at eigenvectors of A. We are saying that this is a matrix identity. All right. So this is true for every x that you take in Cn. That's more important. All right. I have given you the proof. So look at some of the examples here. Example 1. So, let us take A as 1, 2, 1 minus 3. So, P lambda or P of x will be equal to determinant of x minus 1 minus 2 minus 1 x plus 3, I hope I am correct, which is equal to x square plus 2x minus 3 and minus 2, which is same as x square plus 2x minus 5. So, this implies that a square plus 2a minus 5 times identity is 0. Fine. Is that okay? This is what you get. Now, recall minus 5 is nothing but determinant of A. All right, just look at this. So, minus 5 is determinant of A, implies A inverse exists. So, I can multiply this by A inverse, multiply by A inverse. This will imply that A plus 2 times identity is equal to 5 times A inverse, implies A inverse is equal to 1 upon 5 times A plus 2y. Is that okay? So, we are able to say that A inverse whenever it exists. So, this part tells me that as an application of this or the understanding of this, it says that if A inverse exists, then A inverse belongs to linear span of I, A square till A n minus 1. All right. So, you are able to say that A inverse is also in the linear span. So, let us understand what I am trying to say here. What I am trying to say here is that I have this matrix Mn of C, which is a vector space of n cross n matrices over C complex numbers. Dimension of this vector space is, what is the dimension of this vector space? Recall, this is n square. Why it is n square? Because its bases are going to look like E11, E12, E1n, E21, E22, E2n, En1, En2, Enn, and what is E1? E12 is nothing but the matrix 0, 1, 0, 0, 0, 0, 0, 0, 0. This is the matrix E12. All right. So, recall that part. We have done it very early at some stage. Fine. So, this is the vector space. Since it is a vector space, there is an A here in this. I would like to look at what is the linear span. So, given this vector space, I write V as this. A belongs to V. So, I want to look at linear span of I, A square, A cube all the way till infinity. All right. Fine. So, I want to look at the linear span of this. The Cayley-Hamilton theorem says that Cayley-Hamilton theorem implies, all right, theorem implies that I can write A to the power n as minus of A n minus 1 A to the power n minus 1 plus so on plus A1 of A plus A0 of identity. So, the whole space here, this linear span is nothing but this is equal to linear span of I, A square till A to the power n minus 1. I do not have to go beyond n minus 1, even though I want to find linear span of I, A square till any power of A, I just have to restrict myself to understanding I, A square till A to the power n minus 1. I do not need to go beyond that. Is that okay? That is very, very important for me. And that is a crucial thing in saying that if I look at the dimension of this space, it has how many vectors? 1, 2, 3 till n. So, dimension of this is less than equal to n minus 1. Fine. That is important. So, there are things that it tells me. It tells me that this linear span of this, which has infinite number of powers of A, there is no need to go to all the infinite powers. I just need to go till the power n minus 1. That is one thing it says. It also tells me that its dimension is less than equal to n, not n minus 1. I wrote it wrongly because there are n vectors here. There are examples where you can show that this linear span, this dimension is strictly less than n. For example, for the identity matrix, its dimension is only 1, all right, the identity itself. So, try that out yourself. Let us look at some more examples. Example 2, take A as 0, 0, 1, 0, 0, 0 and 0, 0, 0. Let us look at this A. Then you can see that P lambda or P of x for me is determinant of xi minus a will be equal to x cube. So, this implies a cube is 0, that you can check. This is the Kelly-Hamilton theorem, but what you can verify here is that a square itself is 0, but in this case, in this example, a square is 0, all right, fine. So, therefore, what we are saying is that in here linear span of a square and so on, Kelly-Hamilton theorem says that this is same as linear span of a square, because a cube is 0, fine. It has to go only till n minus 1, so it can go till a square only. But in this example, we see that this is same as linear span of I and a and nothing else. Is that okay? That is more important. Anyway, this is not invertible, but this is what you have. You can look at another example 3, where take A as, which is invertible 1 1 0 0 0 1 0 0 0 1. If I look at this, I can write like this part, sorry, not this one, but like this. So, I would like you to see here is that 1 is an eigenvalue, 1 is an eigenvalue, repeated thrice, repeated 3 times, fine. So, by Kelly-Hamilton theorem, what I can say is that a minus I whole cube will be 0, fine, because characteristic polynomial is x minus 1 whole cube. This is what P of x is. I can get this part, but I would like you to verify that a minus I square itself is 0. All right, so try that out. So, exercise, try that out yourself. Is that okay? Fine. Some more implications for what we have seen is that if A is a nilpotent matrix, then there exists a k such that a to the power k is 0, fine. Can we say k has to be less than equal to n? That is the question, all right. Initially, we do not know what that is, but we would like to say that k is less than equal to n. How do I do that? So, the idea is very simple, that since A is nilpotent, implies its eigenvalues are all 0, implies its Px, the characteristic polynomial, is x to the power n, and therefore, by Kelly-Hamilton theorem, I know that a to the power n is 0. Is that okay? And therefore, I get that k has to be less than equal to n, fine. Another important application of this is what is called in graph theory. So, take A to be the adjacency matrix of the graph, all right. I just take this adjacency matrix of the graph. What I see is I will compute a to the power n. What we have seen that a to the power n is nothing but a n minus 1, a to the power n minus 1, plus so on, plus a1 of a plus a0 of I, fine. So, look at this expression. If I know, all right. So, look at this. What we want to say is that G is connected, the graph is connected. It means that graph is connected means, so this corresponds to saying that for every vertex I and j, all right, there is a walk or path of length k, all right. What this part tells me that I just need to go till n minus 1. So, if I and j are connected, then the path that I want to look at is only till n minus 1. The distance can be maximum distance between any two vertices of a graph having n vertices will have n minus 1. That is what it says. Is that okay? So, I have given you these ideas. In the next class, we will look at what are called quadratic forms. And I would like you to understand that nilpotent matrices, they play a very important role. We have not done it, but in some sense we have shown here what are called, earlier also I had used the word Jordan forms. All right, fine. So, for matrix A, there is a notion what is called Jordan matrix and things like that, Jordan decomposition. I am not into that because that is out of the syllabus, but I would like you to see here that in this example, you get a minus I whole square is 0. So, if I remove I here from this, I can remove this part, then I am looking at the matrix 0, 1, 0, 0, 0 here, 0 here, 0. This is the matrix I am looking at. This is a nilpotent matrix and its order is 2 because of this extra 1. Is that okay? Similarly, in the previous example here, this is a nilpotent matrix, this is what the example says. So, all the ideas, so whenever I have some matrix A which is not diagonalizable, somehow this nilpotent matrix comes and play a very important role whenever something is not diagonalizable. So, keep track of that. That is all for now. Thank you.